Okay, let's do a pressurized container example here with the unsteady conservation of mass, okay? So what do we have? We have a tank filled with water. We have an initial depth of 0.8 feet. We have some airspace up here of 0.3 feet. And the air is pressurized to 300 pounds per square foot gauge, okay? And the key difference for this particular example is that the container is closed, so the air is not allowed to enter or leave the container. What we're trying to figure out is, at this instance shown, what is the initial outflow velocity and flow rate? I'll just give you the flow rate. And then what is the water height when the flow stops? And I guess related to that is, why would the flow eventually stop? And we'll talk through that in a second, okay? So the initial outflow rate. So the difference for this problem is that we have pressurized air above the water, and that will create an additional driving force to force the water out of the hole because it has a positive gauge pressure, okay? So you can think about the driving force that's forcing the water out of the hole as being the sum of the pressure above the water plus the elevation head. If the pressure was negative above the water, negative gauge, then that would reduce the driving force from the water. But basically, if you apply your energy equation from the free surface, where you have the pressure equal to the air pressure, down to the free jet, where you have atmospheric pressure, you can find that the discharge out of the hole here is equal to the discharge coefficient times the theoretical discharge, which is the outflow area, times 2g. And then this is the pressure difference between the air above the water and the atmosphere. So basically, this is the gauge pressure of the air, and we add that to the water depth h. So if we didn't have any pressurized air, basically this term would be zero. The air pressure above would be open to the atmosphere, and this would be zero. We'd have our usual square root of 2gh, but because we have pressure, positive or negative, you have this additional term here. And it's important to note that this term could be either positive or negative, depending on whether the gauge pressure up here is positive or negative, okay? So if you plug in the numbers for this instant that we're looking at here, you get that the initial outflow out of this container with the pressure of 300 pounds per square foot gauge and the water depth of 0.8 feet is about 6 times 10 to the minus 4 cubic feet per second. So a pretty small outflow, but it is a very tiny hole here, okay? And so now the question is, what happens over time? And so initially we have this pressurized air that's contributing to the driving force for the water being forced out of the hole. But at some time later, we have the same air meaning the same mass of air, but it's occupying a much bigger volume, right? We've drained water out of the tank. The water can leave the tank, but the air can't. And therefore, we have reduced the pressure of the air, okay? And the driving force of the air above the water has actually been reduced, and therefore the flow would be expected to go down even more because you have less pressure up here, okay? And so if you think about the final state might be somewhere down here. The subscript F means final. And if we look back at our equation for the flow out of that hole, the final state is where we no longer have any flow out. And the reason we no longer have any flow out is because we get into a negative gauge pressure situation for the air up here. So basically you have negative air pressure here, negative gauge below atmospheric, adding to a positive water elevation here, and they sum to zero. So when this term here sums to zero, basically the outflow will shut off. And we know this from everyday experience, right? When we have a container and we turn it upside down, if there's no hole poked in the top of the container, the liquid will stop to drain, right? And so you poke a hole in the top of the container and you restore atmospheric pressure above, and you just have a nice flowing system. But if it's closed, eventually the pressure up here is going to get so negative that it offsets the elevation head here driving out the flow, and this thing will shut off. And so how would we quantify that? Well, in order to quantify that, we need to say something about the air expansion, okay? And that gets a bit into how does the air expand? There are different ways to model air expansion. The simplest way is to think about isothermal expansion, which basically means that the mass of the gas in here is constant, and the temperature is also constant. And if you apply the ideal gas law, you can derive very quickly that the pressure times the volume for isothermal expansion is constant. And if it's constant, we can evaluate that at the initial state, the initial pressure, P0 being the initial 300 pounds per square foot gauge. This has to be an absolute pressure, though, if you're working in the ideal gas law, and this initial volume. But that is essentially the constant, and for any other time, this pressure times volume will be equal to this initial pressure times the initial volume. And so if we rearrange that, we can show that the air pressure above the water at any instant in time is equal to the initial pressure times the initial volume divided by the volume at that instant. And we can rewrite the volumes using the geometry of the container. It's very simple geometry, right? So basically the volume of the air above is equal to the surface area of the tank times this elevation here, this headspace. I'm calling it L0. But you could also recognize that the L0 is equal to the entire height of the container minus the water level at that particular time, okay? So if you plug that in for the volumes, the initial volume being subscript 0 and the volume at some later state, you can derive this expression here. This one follows exactly from this one, where we've replaced this initial volume with H minus H0, which is basically this L0, and then the final volume, or the later volume, which is just some L, or equivalently some H minus lowercase h, the water depth, okay? So this expression allows you to account for the air pressure at any instant if you know what the water level is at that instant in time. And if I'm using a subscript here, F, I'm talking about the final state. So the final state, we have our expression here, and we have this idea that the flow is going to stop when this term goes to 0. Basically, you have a negative enough gauge pressure in the air that it offsets the H. So if I'm using a subscript F for the final state, this is our final air pressure in absolute minus the atmospheric pressure plus the final water elevation. That should be equal to 0, and that will be when the flow shuts off. We had our isothermal expansion equation where we have this final air pressure is equal to the initial times the ratio of the volumes. That gets inserted into this equation here, so we take this air pressure and put it into here. And if you rearrange that equation or just plug it in, you basically get this one here. And you notice that of the things in this equation, we know the initial pressure, we know the gamma of water, we have the overall height of the container is 1.1 feet, I believe. The initial height of the water is 0.8 feet. Atmospheric pressure is 2,000 pounds per square foot. The initial pressure is 2,300 pounds per square foot absolute for the initial pressure of the air. And the only other unknown in this equation is therefore the final water elevation. So this equation is nonlinear. It's basically a quadratic, and if you want to solve it, you multiply through by the denominator in this first term here, and you have a quadratic equation with respect to HF. You can solve that using an online quadratic equation solver or the quadratic formula. And if you do that for the numbers that we have for this particular problem, you'll get that the final water elevation is 0.75 feet. And if you do a spreadsheet calculation, you'll find that that occurs in about 35 seconds. And just to back up a bit as to how you would do the spreadsheet calculation, it would look something like this, where you have essentially columns for time. You have your initial water level here, 0.8. No inflow. The outflow is given by your discharge coefficient times the square root of the 2g times the pressure term plus the elevation term. That's coded up into here. And from that, you can infer the dHdt, the rate of change of the water surface elevation, basically is Q in minus Q out divided by the area of the container, which is a half-foot diameter container. And if you track this simulation down, eventually you'll get to a point where after about 35 seconds for these particular numbers, you'll notice that the water level gets to that 0.75 final state, and everything else kind of shuts down. Your final gauge pressure, or final absolute pressure, is 1953 pounds per square foot, okay? So getting back to that occurs in 35 seconds, more or less, okay, so pretty quickly. So just to summarize, we started with 0.8 feet of water. We had pressurized air that was pressurized to 300 pounds per square foot above the atmospheric pressure, which was 2,000. And we end up in this final state where we have a negative 47 pounds per square foot, and that's a gauge pressure, and a 0.75 feet. And again, this final state is where you have a negative gauge pressure adding to the head from the elevation of the water to be 0. And that's when we have this no flow condition there, okay? So pretty cool problem, and it's something that happens in everyday life. And again, it's why we need to poke a hole at the top of a container. And this gives you the equations to actually solve that problem mathematically and to do some estimates. So hopefully that's been a useful video, and good luck solving problems.